Thanks for coming. Today we're fortunate to have Steve Swanson here from UCSD to talk about non-volatile memories. I met Steve at a conference that he hosts there at UCSD, a non-volatile memory conference, and they're having the next one in March. So if you find the topic interesting today, you might think about attending that workshop. I'll turn it over to Steve and let him talk with us. Thank you.
All right. Thanks. Thanks for having me here today. So I'm going to tell you about some of the work that we've been doing at the Non-Volatile Systems Lab at the University of California, San Diego, which is a lab I run with another faculty member, Rajesh Gupta, and of course a whole bunch of graduate students who actually do all of the work. And the purpose of the Non-Volatile Systems Laboratory is to look at emerging solid-state non-volatile memories and understand what their implications are going to be for computer systems. And we do a bunch of different work kind of in that very broad area. And today I'm going to tell you about a prototype SSD that we've built that targets some of the very fast non-volatile memories that will be coming down the pipe in the next few years that will probably replace flash memory in some applications. So just kind of by way of motivation to get us all on the same page, you know, we're kind of at the cusp of a revolution in the way that computers store and access data. And we can sort of get a handle on this by looking at the change in I/O performance over the past few years. So for the past several decades, we've used hard drives. Hard drives are pretty slow. If you're doing random 4 kilobyte reads, in this case I've shown measurements for a 4-disk RAID array. The latency is going to be about 7.1 milliseconds, and the sustained bandwidth that you can get will be around 2.6 megabytes a second. Now, since the hard drives were introduced, processor performance has increased by a factor of maybe 200,000 or so. Hard drive performance has improved by a much smaller factor. But that's about to change. And if we look at sort of the current state of the art in storage, which is a PCIe-Attached flash-based SSD, that'll give you about 100x relative to disks in both latency and bandwidth. And so that's pretty good. But if we look a little farther down the road and look at some of the memory technologies like phase change memory or spin-torque transfer memory that might replace flash and will be a lot faster than flash and put that into the same kind of device, we can get latencies down to about 12 microseconds and our bandwidth up to 1.7 gigabytes a second. That's actually more limited by the interconnect than by the actual memory technology. So that's a factor of about 6 to 700 in terms of latency and bandwidth relative to disk. And what's interesting about that from a computer architect's perspective, which is what I am, is that on a compounded basis, that's about 3x per year in terms of latency and bandwidth improvement, which is much higher even than we saw in sort of the heyday of Moore's law when processor performance was increasing very, very quickly. And so this is a very abrupt and very large change in one particular aspect of computer system performance. And we can expect that, and we've seen, as we built this prototype, that has impacts all the way throughout the rest of the system. I should also say I'm happy to take questions during the talk. I probably don't have enough slides to fill the whole hour slot, so if you ask questions, it'll make it more interesting for everybody. So to just take a look at latency in particular and understand why this might change systems pretty fundamentally. I've taken here the latency for a 4 kilobyte random write and broken that down into 3 different components. The green is the hardware access time, the red portion is the file system, or is the operating system time, and the blue portion is the file system time. The horizontal axis is microseconds on a log scale. And what you can see is that for the disk, the hardware access time is about 6 orders of magnitude larger than the software access time. And as we move to flash, which is sort of where we are now, it gets better, but it's still about 4 orders of magnitude. So nothing has really fundamentally changed about the system. Software is still very cheap compared to the hardware costs. And as we move to something faster like PCM, which is what I'm going to be talking about today, there really is a profound shift in where the latency lies. So now we're at a point where the hardware cost is on the same order of and maybe even smaller than the software latency that we would see in a conventional system. Yep, go ahead.
How did you come up with the time taken by file system and OS with the PCM?
So these are measurements off of the prototype system I'm going to talk about today. Oh, sorry. The question was, how did we get the breakdown for the PCM memory technology? And so this is off of the prototype I'm going to describe, measured values. All right, so how would we go about architecting a solid-state drive for one of these fast memory technologies? So what we found is that both the hardware and the software components of the system are going to limit performance in different ways, and so we'll need to deal with both of them. And that getting the interface between the hardware and software is very critical to getting good performance out of the system. If we can do that, if we can co-design them together, we can get increased bandwidth, significant decrease in latency, and also a large increase in concurrency. As also we'll see, we can actually reduce the amount of CPU time required to do I/O as well. So with that sort of motivation out of the way, this is the outline of what I'm going to talk about. First, I'm going to tell you about our prototype system. It's called Moneta. I'll tell you about its architecture and how it works. Then I'll describe some of the optimizations that we've made to Moneta to try to get the kind of performance out of it that we would like to see. I'll talk about a little bit of application level performance analysis, and then I'll wrap things up. So this is Moneta. This is the storage architecture that we've built. And to sort of give you a tour of Moneta, I'll go through the life cycle of a request as it's made from the host side. So Moneta connects to the host system over PCIe, which provides you can think of it as two interfaces. One is a programmed I/O interface, and the other is a DMA interface. So to issue a request, the host machine issues a PIO write, which transfers information about the request to hardware. That goes into a request queue. When there's room in the scoreboard, the request will go into the scoreboard, and the scoreboard is going to keep track of the access's progress through the rest of the system. In this case, we're looking at a write, so we've got to grab some data from main memory from the host. We do that by allocating a transfer buffer to hold that data, and then we talk to the DMA controller, which will go pull it out of main memory. Once we've got it, we can push it over our the network interface that hooks up to a ring network that runs at 4 gigabytes a second and connects to 4 independent banks of our non-volatile memory. In this case, I've drawn it as phase change memory, but it could be any of these fast non-volatile memories that will be coming down the pipe. We do that transfer. The ring tells us when it's finished. When the scoreboard sees that the request is complete, it sets some status registers and then raises an interrupt, so that the host can come back and check the status of the commands and complete the commands in the operating system. Above the hardware, there's a bunch of other layers. There's the PCIe interface. So our prototype uses a by 8 PCIe 1.1 interface, which gives us 2 gigabytes in each direction for reads and writes. On top of that, there's a driver. Then there's the rest of the OS I/O stack, a file system if one is present, and of course at the top the application. And all of these different layers are going to add latency. We're going to focus on the software pieces and how we can minimize that latency as much as possible. So these memory technologies I'm talking about, just to give you an idea of what memories Moneta is built to work with. We're looking at these fast non-volatile memories, and the idea here is that they should be memories that have DRAM-like speed and also a DRAM-like interface. And there's a bunch of different memories that are sort of competing to sort of be the memory that we use in applications like this. Things like phase change memory, spin torque transfer memory, the Memristor, racetrack memory. There's a whole bunch of them. Moneta is more or less agnostic about which memory technology you use. I'll talk a little bit about our sensitivity to things like device latency later. We're just building for one of those technologies. Here, for the results I'm going to present today, we're modeling phase change memory, which is sort of the nearest in of these advanced non-volatile memories. We have prototype phase change devices in our lab, so you can actually buy these. There's, someone just cited that there's someone shipping a cell phone with a phase change memory device in it. It requires a little bit of wear leveling, much like Flash, but the wear leveling is much simpler. And just sort of for completeness up here, we use something called start gap wear leveling, which was presented at an academic research conference last year. So this is our prototype that we've built. The system is built upon something called the B3 prototyping system. It's a box you can buy. It has 4 FPGAs and 64 gigabytes of DRAM. We use the DRAM to emulate the fast non-volatile memories that we're interested in. The box connects over PCIe 1.8. Our design in the FPGAs runs at 250 megahertz. And the way that we emulate the PCM memory is by adjusting the memory timings inside the memory controller. So for this work, we've modeled a read time of 48 nanoseconds and a write time of 150 nanoseconds, which matches kind of aggressive projections for where PCM might be in a few years. The current devices are a good bit slower. But we can modify the timing so that this is modeled at a very high degree of accuracy. So if we had a memory like this, we can be pretty certain that this is how such a device would behave. So that's sort of the Moneta architecture, the whirlwind tour. Now I'm going to talk about how we went through optimizing Moneta and the changes we had to make to get good performance. So when we built the first version of Moneta, we ran it underneath the standard Linux I/O stack. We just built a block device, built a low-level block device driver, and then ran some I/O benchmarks. And what we found was that the performance was actually somewhat disappointing. So our measurements showed that our hardware latency for a 4 kilobyte access was about 8.2 microseconds, but the software latency was about 13.4 microseconds. And this includes a bunch of stuff you can see on the stacked bar graph on the right. There's the overhead of getting in and out of the operating system, the I/O scheduler, the copy you have to do for the data, issuing the request, processing the interrupt, and also waiting around for the request to finish. And so what we want to do is try to figure out how we can reduce that software overhead because it was really limiting our performance. And so the first thing we do was to get rid of the I/O scheduler. And this is a pretty common optimization. Other state-of-the-art solid-state, flash-based solid-state drives do this as well. The problem here is that in the standard Linux I/O stack, when a thread wants to make an I/O request, the thread enters the kernel, puts a request onto a queue, and then goes to sleep. Another thread wakes up and then pulls it off the queue and actually issues it to hardware. There's two problems with that. One is that you end up paying two context switches to issue the request, and the other is that the I/O scheduler thread can have a serializing effect on the accesses that go out. Both of those are bad. So if we just get rid of the I/O scheduler completely, so that the thread that comes in from user space actually issues the request, performance improves. We get about a 10% decrease in latency, and we also get an increase in concurrency, which we'll see in a couple slides. But that turns out to be important as well. The next step was to make our tag management more efficient. So like a conventional SATA SSD, our system has multiple tags, and every request, every concurrent request that's in the storage array has a unique tag. So to make our tag management more efficient, we went through and profiled kind of where it was spending its time, and it turned out it was all about contention for locks. So we improved our lock management code by turning it, the data structure that holds the pool of free tags into a lock-free data structure so that we can access it without acquiring any locks. And then we go through and we index all of the other data structures that the kernel uses to track the request. We index based on that tag number. And so once you've allocated the tag, you've allocated a bunch of other things as well. And the final thing that we did is we used the processor ID as a hint for which tag the thread should try to acquire. And what that means is that if the hint ends up being, if you get the one that you asked for initially, that means that all of the other data structures are already going to be in your local cache on that processor, and so you won't take those cache misses to get that data over to that processor. And this turns out to, we didn't actually realize how important this was until we'd gotten most of the way through this process. But we're at the point now with this optimizations that even a single extra cache miss kind of on the path through the I/O code ends up being a measurable effect on overall performance. So these kinds of optimizations end up having a pretty big impact. The second thing that we did was to co-design the hardware and software interface so that they're a very good match for each other. So in our baseline design, you had to make multiple PIO requests to issue a single I/O operation. And in the driver, we had a lock that would protect those I/O registers so that you would get a consistent request written to the hardware at once. It turns out that lock was limiting concurrency and causing a lot of overhead. So what we did is we compressed down the request word so that a single request would fit in a 64-bit word. And then we can write that as an atomic 64-bit store, and the PCIe request will make sure that it shows up, that they'll be serialized on their way to the hardware. This, combined with the previous changes, means that there's no more locks left in our driver at all. So the threads don't contend for any shared state in the common case. The one drawback is that we lost the DMA address in our request because the DMA address is a full 64 bits. So to get around that, we pre-allocate buffers in kernel space and then write those addresses down to the hardware, and then we index into that table that's stored in hardware to determine where we should read or write data from in host memory. The impact of this, the combination, we get increased concurrency again, and we also get another 10% reduction in operation latency versus the previous version. The final change that we made was to use spin waiting for small requests. So in the standard I/O stack, when you issue a request, you go to sleep and you wait to get woken up by the interrupt that comes back. It turns out that took a fair amount of time. So instead, for small requests smaller than 4 kilobytes, we actually just spin waiting for a flag to toggle that tells us that the request is finished. And that ends up saving a bunch of latency, although it does increase CPU utilization a little bit. Yep, go ahead.
Can you talk a little bit about what implications are from a programmability standpoint of this decision to actually have to preload DMA addresses?
So the question was, what is the impact on programmability from preloading the DMA addresses into hardware? If you're a device driver author, it actually makes things pretty simple. When you go and allocate a tag, you can look up what the associated DMA buffer is, and that's just the target that you use for the DMA. In a conventional driver, there'd be some target that you'd use anyway. Unless you're doing something very aggressive like zero copy, this doesn't really impact things. I'll talk a little bit about zero copy in a moment, and what the implications are from that perspective. From the applications perspective, nothing changes at all. It's still a normal block-based interface.
That has a lot to do with the fact that you still have this model of device driver and some ring buffer.
Yeah, so we're still in that same model. Although we don't this sort of does get rid of the ring buffer. I mean, there's still a series of buffers that you use, but they're allocated more dynamically. So this gives us a 54% reduction in software latency versus the previous version, and also total is a 62% reduction in latency versus the baseline design. And you can see on here that we're down to about 5 microseconds of software overhead from the previous, 13 or 14 or so. Yep.
So if you're spin waiting, why even have an interrupt?
We're actually spin waiting for the interrupt handler wakes up, and so the question is, why are we spin waiting? Why do we have an interrupter for spin waiting? In this work, the interrupt handler sets a flag that the thread is spinning on. You could also issue a DMA from the device to set the flag directly. We're working on that now. That's an optimization we looked at for some other reasons. But it also turns out you kind of need both anyway, because you don't want to always be spinning. So for large requests, spinning is a horrible idea. It's only for the smaller requests that spinning pays off. All right. So this was all latency, but we can also get some good improvements in concurrency and overall bandwidth. So this is our kind of the graph we draw to sort of evaluate our storage array. The horizontal axis is access size, so these are random accesses of a given size. The vertical axis is sustained bandwidth that our array can do, and this is all from user space using an IO testing tool. So the bottom blue line is our baseline design. Performance is pretty poor for small requests. It increases pretty rapidly as request size goes up, and tops out at about 1.7 gigabytes a second. That's sort of the limit of the PCIe bandwidth minus the PCIe overhead. The line at the top is the full PCIe bandwidth, the theoretical peak. And then as we add these different optimizations, we're basically going to push this curve over to the left. So when we get rid of the scheduler, you can see our the performance for the small accesses goes up by quite a bit, as do the requests or the bandwidths for a lot of the smaller request sizes. And then as we add additional optimizations, things get better and better. Here's, you can see for Atomic starts paying off for request sizes at about 2 kilobytes or larger. And then if we have, all of our requests, we get actually a huge increase in IOPS for small requests. And this is because of the increase in concurrency, and because there's less work to do per IOP after we've gone through and made all these changes. The one interesting thing here is the green line for the atomic. In theory, the atomic optimization should increase performance pretty dramatically for the small requests, but as you can see here, it doesn't. And what's actually going on here is that you end up being dominated by the wait time, and so those benefits don't show up until you get the cost of waking up down quite a bit, and then we get better performance. So we can do about 1.5 kilobyte IOPS. Which is pretty good for a storage array. And we think our limitation here is primarily the PCIe bandwidth. If we had more wider PCIe bus, we should be able to get a similar number of IOPS for larger requests as well. And there was a question.
Yeah, what's the concurrency on this?
This is all 16 threads. I should also say this is running on a 2-socket Nehalem machine, so there's 8 cores running with 16 threads for all this data. It's an excellent segue also. So this is a CPU utilization across these different software stacks. So the horizontal axis is the different configurations. The vertical axis is the number of CPUs required to maintain a gigabyte per second of throughput. And so as you can see, for the baseline, it would take about 12 of these Nehalem CPUs to get a gigabyte a second going. And this is why, this is for 4 kilobyte reads and writes. This is why we don't actually ever get to a gigabyte a second at that access size for the baseline. Once we've gone through and made some of these optimizations, in particular removing the scheduler, the CPU utilization drops a lot, and we can do a gigabyte with just about 3 cores. Atomic doesn't have a huge impact, although it gets things down a little bit more. Spin weight, the CPU utilization actually goes up. This isn't so surprising since you're spinning waiting for the request to finish. And so there's some trade-off there to be made about performance and CPU utilization. Go ahead.
In these graphs, are these changes taken individually, or
This is aggregate, yeah. So in all these, this is everything previously, yeah. Yep.
So why is spin weighting affecting 4 kilobytes read writes if you mentioned that you were doing that?
Oh, sorry, it's 4 kilobytes and smaller.
Up
Yeah,
to 4.
up to 4, yeah. Okay. So one common optimization is for making I/O go fast. That's gotten a lot of press in, say, the networking world, is zero copy, where you can actually DMA directly in and out of the user buffers. And PCIe nowadays supports pretty sophisticated memory mapping that allows this to be done with pretty low overhead. We tried zero copy. It turns out that it's faster for us to do the copy in the driver than it is to do zero copy, because if we do zero copy, then we have to write down the DMA address along with the request. So we end up introducing a lock in the hardware. We have looked at also, it's possible to sort of DMA requests out of main memory and so avoid PIO altogether. And that might be a way to get us back to being able to do zero copy efficiently. Another solution would be to have a little bit of support at the processor level. For instance, if we could do 128-bit atomic write, we could get around this problem as well, just because we could write more data down at once. Same if we could, for instance, a similar effect we could get if we had, say, a cache line size atomic write. You could flush and guarantee that all of those, all that data would go out to the memory controller in one go. All right, so that's the optimizations on the interface side and the software side that we've performed to speed things up. But there's also some things to be done inside the Moneta array itself. And one of the things we've given up by making the changes we did to software is, for instance, we've dropped the scheduler. So now there's no handle, the operating system, the system doesn't have any handle on how those requests are going to be scheduled. So if you want to do something like fairness, you're going to have to do that somewhere else, and that ends up being in the hardware. So there's two things that we've looked at here. The first was a pretty straightforward change, and that was that since we have a full duplex PCIe connection, we should be able to get 2 gigabytes going in each direction. But if we do a combined read-write workload, our bandwidth ends up topping out at about 1.6 gigabytes a second, which is about the same as it was for reads or writes on their own. So the solution is pretty simple. We just split our request queue into two, so we have a read queue and a write queue, and then we draw from them kind of in round-robin order. And that guarantees, or if there are reads and writes present, we'll get both of them going, and that'll allow us to use both directions on the PCIe connection. And that ends up having a pretty large effect on overall bandwidth. We can get up to just under 3 gigabytes a second. There's still some, lingering inefficiency there. I'd like to see that higher, and we're working on improving that a little bit more, trying to understand what exactly is limiting our performance. The second change was to do round-robin scheduling between requests to improve fairness. So one of the problems that we observed in some of our workloads was that if one thread was making very small requests, say 4 kilobyte requests, and another request was making much larger, say 512 kilobyte requests, that they would get the same number of IOPS, but that actually means much, much less bandwidth for the smaller requests. And so in order to improve fairness between these kind of competing request streams, we go through and modify our scheduling algorithm a little bit. So the way that our hardware worked, even in the baseline, is that if you had a large request, the scoreboard would sort of take one piece of it and go and process it, and then take another piece and go process it. So what we do now is we take the first piece for a large request, start up processing, and then we put the rest of the request at the back of the request queue. And that means that if there are any smaller requests waiting behind it, they'll sort of get the next crack at the scoreboard, and we'll be able to get better fairness between the competing flows of requests. So if we do this, we get about a 12x improvement for the small request bandwidth without impeding the overall total system bandwidth at all. So we're not really giving up anything to improve the fairness. And I think what this points to, I'm a computer architect. I like to design chips and so forth. So what this means is that all of the many decades of work that goes into I/O schedulers now gets to be redone in silicon. And so we can understand what exactly the right interface is for configuring this, what the right mechanisms are that will let you implement interesting and flexible scheduling policies, to adapt this to the applications you're looking at. So one really simple thing is you might want to attach some sort of an ID to this so that individual threads, the request would look different to the hardware so that it could deal with them differently. Otherwise, everyone's going to end up getting treated the same, which may not be what you want. Yep?
Have you considered looking into what was wrong in the IO scheduler, what was causing all that performance problem?
Oh, the I/O scheduler, it is just the context switches and the serialization. So the first thing you do if you're going to get rid of the I/O scheduler is you go and you Google and you find out that Linux has a no-op scheduler. So that sounds like a great idea. But it turns out the no-op scheduler just does nothing after it removes the request from the I/O queue and then issues it to hardware. And it's actually just the cost of putting the thread to sleep, waking up another thread, dequeuing the thing, just that whole handshaking process, that's where the overhead is. So it's not actually doing anything at all, and it's still a large cost. Yes, well there's a lock on the queue, so you end up serializing on that. And in a conventional disk-based system, there's no point in having multiple threads because you can issue much faster than you can complete, and so you end up with parallelism. In our system, what we found out is that no matter how fast we issued, the request would finish faster than the no-op scheduler could actually issue the requests. That's one of the reasons for the large increase in performance we get with no scheduler at all. So the other thing we looked at, our memory latencies are based on projections, and actually somewhat optimistic projections about where phase change memory will get to. And as you can imagine, the manufacturers of all these different memory technologies all make very optimistic projections about where their particular technology will get to. But we'd like to know how sensitive our design is to increases in latency. So what this graph shows is we vary the memory array latency on the horizontal axis from 4 nanoseconds up to 128 microseconds. And then each curve measures bandwidth with a different number of memory controllers. And so you can see for the very, very fast memories, we can get good performance with a single memory controller. And as things get slower, we just need more and more controllers, and we can maintain the same level of throughput in the system, out to about a microsecond. So even at a microsecond, we don't see any drop-off in bandwidth. Of course, the latency is going to increase by however much your your hardware access time goes up. But the basics of our design still kind of hold, even if memories are a little bit slower than we might ideally like them to be. What's interesting here, and there's some other reasons for this as well, which I'll talk about in a moment, is that you actually there's some tension in the companies that are designing these memories about whether they're going to target a storage application or, say, a DRAM replacement application. And what we found, because of effects like this, as well as some other effects I'll talk about in a moment, is that you actually probably want different devices for those two applications. The access patterns are pretty different between the two. The requirements in terms of durability and how writes complete are pretty different. And also, these applications can be much more latency tolerant. And so perhaps you can make trade-offs in favor of reduced cost or increased density if you know that your application can tolerate a little bit more latency. So this is what I was just mentioning. So there's been a bunch of work in the computer architecture community looking in particular at phase change memory as a DRAM replacement. And there's a couple of optimizations that they propose that do really well in that space but don't work as well in a storage application. So the first thing is something called write coalescing. And basically what this means is that when you open a row in the memory, you hold it open and you keep kind of combining writes for as long as you can. Maybe you'll have multiple row buffers inside your memory chips to prevent you having to go and do an actual write operation, which is a little bit expensive in phase change memory. The problem here, and why this doesn't work for a storage application, is that in a storage application, when the access completes, if it's a write, you need to know that that data is actually in a non-volatile storage location. So if you lose power, it's going to be there. So the idea that you could just sort of hand the data to the chip and leave and hope that eventually it writes it into the storage array isn't going to work in something like Moneta. You actually need to commit things immediately, or at least have some other means of telling the operating system when the write operation is actually completed. The second thing is they looked at varying the row buffer size inside the memory chips. And it turns out this is a source of a whole bunch of power draw inside of DRAMs. And they actually suggested moving to shorter, smaller row buffers to reduce power. That doesn't work as well here either because the accesses tend to be pretty large. So the smallest accesses that we issue are about 512 bytes. It's actually the smallest request that Linux kind of allows you to issue. Well, there's no particular hardware limitation. But most of them are much larger, so they're 4 kilobytes. And so it actually makes sense to have a very large row buffer so that you can write a bunch of data in and do many, many bit level writes in parallel in the array. Let's see. There's also there's some limitations on power. So there's some power concerns with PCM, and it turns out that in our system, because the PCIe bandwidth is not as high as it might be, our total power consumption is actually limited by the PCIe bandwidth because that limits how much work the storage controller has to do overall. So the bottom line here is what I said on the previous slide, is that we need to optimize these technologies pretty differently for storage versus main memory applications. Yep.
You talked about durability. The operating system has mechanisms to guarantee durability of IOs at its issue, like sync and so forth. How do those
So the key here is actually that the way that those facilities, the question was, why can't we just use the operating system's facilities for guaranteeing durability? And the answer is that the way that those systems work is they prevent the writes from completing until the storage device says that they're done. And so that means that it has to be all the way down to either the disk platter or, in our case, into the memory before the storage device can say, yes, this write is actually finished.
There's also a sync operation that will force the device to flush it.
The sync operation, at least as I understand in Linux, actually just works only on the operating system's buffer caches. And so that just issues a bunch of writes to make sure that the buffer cache is clean. They do.
And the only way to clear those is to issue a command to the SATA device.
That's true. And so actually the analogy is pretty direct here. So in order to make sure you have good durability, you have to turn off the write buffer on your SATA device, which guarantees that the SATA device won't tell you that your device, your write is complete until it's either hit the platter or hit the NAND flash. And the same thing applies here. The Moneta can't say that the request is complete until the write to the actual memory device has completed, and we know that if we lost power and look back up, that the data would still be there.
No, you can't issue a sync to the device and it will flush the buffer.
Sorry, you could do that also. You could issue a request that said go and flush everything. That's true. You could do that. Okay. So,
because you can also assume that if you really do want durability, you want that across a number of devices as well, and then you might be able to actually afford mechanisms that say, well, it's okay to give me an early acknowledgement of the write, provided the device can make some reasonable guarantees on power loss that some amount of state will be able to be saved with remaining capacitor.
Right, capacity. We already need a capacitor because you need to be able to complete the request anyway, and that's sort of assumed because you usually would like the requests that are in flight to complete, so you don't just kind of get arbitrary garbage there. So if you're willing to put enough, it's essentially an UPS on the device, then you could play much more fast and loose with the array. The one comment about the sync operation that would certainly work. I'd be a little bit worried, or it would be interesting to know how the performance trade-off comes down. Because if I'm going to be issuing a lot of these sync operations, that's going to take, the round trip time just on PCIe is a microsecond.
You clearly are trading off the performance for durability.
Yep. And maybe, at least on this, well, yeah, you're putting off performance for durability. That's right. All right. So on to the application level. So this is the test system that we've built to test Moneta and compare it to other storage technologies. So it's an 8-core Nehalem machine. It's got a whole bunch of DRAM, which we're not particularly using in this study. We've got Moneta hooked up to it. We have a 4-disk RAID array and a 4 SSD RAID array as well. And we also have an 80 gigabyte Fusion IO card, which is a high-end flash-based SSD. The final thing we compare to is something that's labeled up here as Moneta 4X. So our Moneta device actually has twice as much PCIe bandwidth as all of the other devices we're comparing to. And so just kind of for fairness, we've put this up as well, cut its bus bandwidth in half, and then we can see how it stacks up kind of apples to apples. So these are the applications that we're going to look at. XDD is the I/O benchmarking tool that we use. We do experiments both with and without the file system. Then we look at some database applications. So 2 little kind of database micro benchmarks implemented with Berkeley DB. One that's based on a B tree, the other that's a hash table. And these are very simple. They actually just atomically swap 2 values in a large table. And then we have 2 big scientific workloads that we got from our colleagues at the San Diego Supercomputing Center. The first one is called Biological Networks. It's a very large database. This is a smaller version of a much larger database that encodes a bunch of information about the interactions between different biological molecules. And then you do your science by issuing these very large and complex queries against the database that will sometimes on a hard drive-based system might run for a day or 2. Then the last one is something called the Palomar Transient Factory. This is a sky survey application where they're taking a picture of the entire sky, or at least large portions of the sky each night, and they look at each point of light and they're trying to determine whether that piece of light was there previously. And it's pretty cool, actually. If they find something new and are able to determine that it's interesting, they can, in real time, focus a whole bunch of other instruments from all over the world onto that spot in the sky to see what's going on. And so these requests are actually very small, they're very simple, but there's a whole lot of them and they have a real-time component to them. And so performance is very critical. And actually on our system, for at least this database size, we can take this from offline to real-time by running it on Moneta. The final set of applications are memory-hungry applications. So these are memory-intensive codes, and we restrict the amount of DRAM in the system and to force them to page to the Moneta device. And this is an application that's getting this kind of application is getting a lot of interest in the supercomputing community, where they have extremely large data sets and would be willing to sacrifice actually a fair amount of performance to reduce the enormous costs in terms of DRAM. So if you have a terabyte of data you want to work on, right now you end up getting a very large supercomputer that has a terabyte of RAM, or pardon me, petabyte. You'll get a very large supercomputer with a petabyte of RAM, and you don't actually need that much compute. If you could buy that back with a solid-state memory, you could do it on a much smaller system. And they're building a system like that at SDSC. So this is the XDD bandwidth comparison. This is just raw bandwidth for reads and writes combined across all of our memory technologies. The higher bit here is that even when we restrict our bus bandwidth to match that of the Fusion I/O drive, we're still a little over twice as fast. And then we're much faster than the other technologies. We can also see here that our performance scales pretty well with the bus bandwidth that we have. So between the 4x and the 8x versions, we get about twice as fast in terms of bandwidth, which is what we'd expect. This is a slice through that data, again without the file system, looking at both large accesses and small accesses independently. And the reason I put this up here is so that we can see the effect of the file system, which I hope you can see. So for the large accesses, the file system doesn't have much of an impact for any of the technologies. But for the small accesses, it turns out, especially for writes, that the file system is actually pretty detrimental to overall performance. And this is, we're looking at this now. We suspect that it's the kinds of inefficiencies we saw in the rest of the I/O stack playing out in the file system. And so this is one of the places where there's clearly needs to be some more work. If you want to do small writes, the file system is not your friend. Go ahead.
So when you're doing writes 4K, writes, is that all going to the same file? Or
This is going across the entire device. This and one large file. Yep.
Okay.
Yeah.
So one large, when you're doing run with the file system, it's just one large file.
It's one large file, but XFS is pretty good about concurrent access to a single file. So it should be okay. If you do this on EXT anything, it's a disaster. But it's interesting, if you do across many files, EXT is not so bad. So these are the graphs for the database and the paging workloads. So in each of these, I have our different storage technologies, and the performance is all normalized to the disk. And then the blue bar on the far left of each group, that's the raw I/O performance. And so what we would like to see is that the application level performance would more or less track the raw I/O performance. That would mean that all the money that we're going to be spending to buy Moneta, if we decided to buy Moneta, would be translating into a good increase in performance. And this is on a log scale. And so what we see is that for the slower memory technologies, it does pretty well. You get more or less application level performance back that's about the same as the raw I/O performance. But for Moneta, that's really not the case. And there's about a factor of over 10x of performance that's sort of left on the table there. And this is, again, probably the same kind of software inefficiencies that we saw in the operating system layer that we just need to go and attack in the database world and potentially in the paging system, if that makes sense. And so this is just sort of motivating future work in the area. And clearly there's a lot of work left to be done if these are really going to pay off in a big way. So to wrap things up, these non-volatile memories are coming, and they're coming pretty quickly. We've built Moneta to try to understand what the impact of them is going to be if you try to build a solid-state drive out of them. We found that the interface and the microarchitecture are both critical to getting the kind of performance you'd like to see, but there's a lot of opportunities left to make optimizations above the hardware level, and also to move pieces of the software into hardware. The limitations, the things that are left on that stack of latencies are the OS protection overhead, so getting in and out of the operating system and the file system. Both of those present some really interesting research challenges about how to eliminate or at least minimize those costs. And so there's a bunch of really interesting open questions about these SSDs and the systems that they interact with and how those should all be designed. And there's all my students who actually did all of the hard work, and I'll take any questions.
So if you, instead of using DRAM on your board, hook in actual current hardware, what would be speeds approximately?
So that's a good question. So we've just, we're in the process of building some DIMM-shaped cards that hold some of the prototype memories that are available. The performance obviously varies with the memory technology. The current PCM devices that you can buy are pretty slow. The write times are in the many microseconds. The read times are reasonably fast. So I think we're going to see a very asymmetric performance when we get that up and running. And then, you know, as they keep optimizing those technologies, it should get closer to what we've seen here. Realistically, unless you're pretty close to the density of at least DRAM and maybe even of flash, and your performance is pretty good, definitely much better than flash, your technology is not going to really go anywhere. And so that sort of sets some, you know, the area of interest, and if we're outside that area, then the technology effectively doesn't exist. Yep.
You mentioned you were looking at other technologies to reduce the operating system overhead. Can you elaborate a little bit on that?
Well, there's a couple of obvious things you can do. One, if you have an application that where it'll work, you can export the interface directly to user space by just mapping those PIO pages into user space. And that'll eliminate all of the file system overhead, because there's no file system anymore, and all of the operating system overhead. Well, almost all. You still need to have some way of doing completion. So you're either going to be spinning, waiting on a DMA completion, which we talked about a little bit earlier, or you'll have to forward interrupts from the OS into user space. Either of those are possible. You're obviously limited in the applications where that'll work. Databases, it should work fine. They're usually, well, if they were rewritten, they like to run on bare metal anyway. But for more general applications, there's open questions about how you do protection and so forth in that kind of system. Yep.
So things like PCIe and all that are designed and evolved, I guess, based on how fast the stuff is on the other side of that bus
Yeah.
are, right? And I think your experiments make it pretty clear that a lot of, at least some of the memory technologies, seem to be actually be bad fit for how heavyweight and slow that particular interface can be. Have you had conversations with the CPU manufacturers, for example, these guys about sort of what are their thoughts about this, or do you have suggestions for them what these interfaces should look like?
So with respect to PCIe, it is a little bit clunky. The biggest problem is latency. The graphics folks are making sure the bandwidth is nice and high, which we could leverage pretty nicely. And you could probably shave a little bit of time off the latency, but there's some fundamental limits about even the hardware that does the serial communication and so forth that you're going to run into. The other place to put it is on the DRAM bus, and that gets a lot of attention also. I think there's certainly opportunities to put it there as well. One of the things that we've found is that in our experiments where we've taken a lot of DRAM and built just a block device out of that as a RAM drive, is that the I/O requests end up competing and interacting sometimes in negative ways with other memory requests because they're both contending for the same bus. So there's definitely some advantage to having the I/O on a separate bus from the normal DRAM because they have very different access patterns. The accesses are larger. There's maybe better locality for the I/O. So one simple thing you could do, in Nehalem, the chips we have 3 different memory channels on each core. So maybe you designate one of those as the I/O channel, or you configure them somehow so that you steer all the requests or reconfigure the memory controller or something to make that particular memory channel a little better behaved for storage kinds of applications. I think there's still going to always be a place for something like PCIe, and the reason is that it makes it possible to connect multiple servers to a single box of memory, which a lot of storage applications would benefit from. And you can do, it's vastly faster to connect 8 machines over PCIe or over Fibre Channel or something else to a box of memory than it is to put a server in the middle that's going to pull it out and do all of the server kinds of things. And things like parallel NFS and so forth make it possible to do that kind of direct access pretty easily. So I think they're probably going to coexist. I think you're probably also going to get better scalability in terms of capacity from something like PCIe. I don't think we're ever going to get, a terabyte of anything on your DRAM bus. Or if we get that, then I'll say we're not going to get 64 terabytes of anything on your DRAM bus. And so there's always going to be a space for that kind of device.
There are more questions.
All right.
Thanks so much.
Thanks.
For coming. Let's thank you.